Good afternoon. My name is Tania Esquivel, and I am pleased to present my work entitled Prototype and Design of a pH and Humidity Sensor for the Treatment of Chronic Wounds and Burns. Well, chronic wounds and burn injuries represent a major clinical challenge worldwide. They are associated with long healing times, risk of infection, and high healthcare costs. One of the main difficulties is that with the wound environment is highly dynamic and can change rapidly depending on the patient's condition. Therefore, continuous monitoring of pH and humidity is extremely valuable. Let me begin by highlighting why these two parameters are so important. As you can see in the introduction, for the pH, healing wounds usually move towards a slightly acidic to neutral pH. In contrast, wounds that remain alkaline are often infected or delayed in healing. Therefore, pH serves as a biochemical indicator of wound status. For the humidity, while maintaining the right moisture balance is critical. If a wound is too dry, re-epithelialization slows down, and if it's too wet, maceration and bacterial growth can occur. Monitoring these two parameters simultaneously and in real time could give medics valuable insights into wound healing progression, allowing for better decision making and personalized treatments. For the objectives of this work, are to design and develop a flexible sensor capable of simultaneously monitoring pH, humidity, and temperature in chronic wounds and burn injuries to evaluate the sensor's performance in terms of sensitivity, stability, and suitability for clinical wound monitoring, and to contribute to the improvement of wound healing assessment by enabling real-time and localized physiological measurements. Let me now describe in more detail how the sensors were fabricated as illustrated in the figures of the poster. Well, for the pH sensor, the sensor layer was based on polyaniline, a conductive polymer that changes its electrical properties depending on the hydrogen ion concentration of the surrounding medium. So, this polymer is sensible to the pH. Well, it's sensible only on its conductive form. That's why it's important to go to a functionalization to go from the emeraldine base that it's not conductive to the emeraldine salt that it's conductive. As you can see in the design, um, there's a flexible paper. It's acetate. There is the working electrode and the reference electrode. These are the two important parts of this sensor. Well, for the working electrode, first the emeraldine base was synthesized and then converted into its conductive form, emeraldine salt, through protonation using hydrochloric acid. As you can see, we dilute panic, EB, and DMSO. It's a solvent, an organic solvent. Then we add hydrochloric acid. We centrifugate. Then we add aniline. It's the monomer from polyaniline to dissolve the polyaniline. And then we deposit a drop of pani and the aniline into the silver substrate and to let the electrode more stable on the silver, we use a cold plasma treatment. And that's how the working electrode was made. Then for the reference electrode, well, and there's deposition from silver chloride, and from electrolytic cell, we deposit this thin film. And then we add an electrolyte and resin solution. It's mixed and then it's added to the electrode reference. And this is used to seal the electrode and maintain it stable and trustworthy along all the measurements. So the working principle for this sensor is that when the sensor makes contact with the wound environment, the pani layer undergoes protonation or deprotonation depending on the pH. If it's acid, then it's protonation. If it's alkaline, then it's deprotonation. And this results in a measurable potential difference, as you can see, between the electrodes, and that's what we can sense through electronics. Now for the humidity sensor, we dilute polyvinyl alcohol into deionized water, and then we add a potassium hydroxide solution and let it dry at room temperature for some days. And this forms a porous membrane sensible to humidity. As you can see in the design, the middle part, it's the porous membrane from PBA and KOH. They are covered by a non-porous material and by a porous material to let the sensor breathe. So the working principle is that it's based on the fact that as humidity increases, water molecules are absorbed into the polymer. There's an initial chemical absorption by chemical bonds from water to the porous membrane. As the porous membrane is hydrophilic, there are bonds formed there. And then there are subsequent physical absorption by a reaction called the Grotthuss reaction. It's like a chain reaction in which there are some layers of water that continuously forms. When there's enough water, then the liquid electrolyte dissolves and this forms an liquid electrolyte. This increases its ionic conductivity and reduces the overall resistance of the film. And that's what we can sense through electronics. For the electronics part, well, there's first of all the signal acquisition, sorry, where the raw electrical response was collected, then signal amplification to improve measurement resolution, and then we go through a microcontroller, a PIC, and this is to process and digitize the signals in real time. This is like the model. Nowadays, there's a physical model, and it's little and practical. So together, this methodology enables us to build a flexible and multifunctional sensor that can be directly applied to wound surfaces, recording pH and humidity changes dynamically and simultaneously. Now, for the testing procedure, the humidity sensor was tested by exposing it to controlled humidity chambers and measuring its resistance. And the pH sensor was tested with standard buffer solutions ranging from pH 4.2 to 9.0. And the reference electrode was compared to a commercial electrode from a laboratory pH meter to determine the stabilization time. All data were analyzed to establish correlation, sensitivity, and linearity. And for the last part, the results and the conclusions. Well, moving to the key results for the humidity sensor, as you can see in the first graph, the resistance decreased significantly as humidity increased. The experimental data fit very well to an exponential model with a correlation coefficient of 0.9906, showing high sensitivity and reproducibility. As it's what I'm showing you at the first graph. And now for the pH sensor. Well, the sensor showed a stable and distinct voltage output across the tested range of pH, that it's 4.2 to 9. Well, there, here in this graph. And importantly, it demonstrated a linear inverse relationship, as you can see in the third graph, with a slope of approximately minus 35.15 millivolts per pH unit, and an excellent correlation coefficient of 0.99399. And for the reference electrode, stabilized after about 30 to 40 minutes, which is promising compared to commercial electrodes. The results confirm that each component of the system performed well, and together they provide reliable monitoring of key wound parameters. Well, as you can see for the reference electrode graph, it's constant or stable at 30 minutes, but before the 30 minutes, it is not that variable. As you can see, it goes from minus 2.5 millivolts to 1, so it's not like a big change that can affect or mess with the sensor measurements. So it's not a big deal. And well, now conclusions. This prototype demonstrated that the feasibility of developing a flexible, low-cost, and multifunctional sensor for clinical wound monitoring. The device successfully measured pH humidity with good sensitivity and stability. Looking ahead, future work will focus on reducing the stability time of the reference electrode, integrating wireless data transmission for remote monitoring, and, well, ultimately, this type of technology could contribute to faster wound healing, better infection management, and improvement patients' quality of life. That's like the more important part of this project. And that's all. Thank you very much for your attention. I will be happy to discuss any questions or comments you may have. Feel free to comment, suggest, or ask anything. Thank you so much. Bye.